Hello and welcome to Additive Insight, the original additive manufacturing podcast, and your source for news, interviews and comment on the latest 3D printing and AM intelligence, brought to you by TCT Magazine. I'm your host Sam Davies, and today I'm joined by Norsk Titanium VP of Engineering, Jack Adams. Norsk Titanium is an FAA-approved and OEM-qualified supplier for structural titanium parts made with its high deposition rate additive manufacturing technology. The company utilises its Rapid Plasma Deposition process to produce commercial aerospace and defence components, with Airbus, Boeing and General Atomics Aeronautical systems among its publicly announced partners. Throughout our conversation, Adams discusses the fundamentals of the RPD process, the evolution of its Merke machine series, and the applications Norsk is enabling. We also discuss the company's R&D activity, emerging application opportunities, and what comes next for the company. If you like what you hear, don't forget to subscribe wherever you get your podcasts. You can also head over to tctmagazine.com to subscribe to the TCT membership platform and receive more additive insight via our print and digital offerings. Jack, welcome to the Additive Insight podcast. We'll come on to talk about Norsk's Rapid Plasma Deposition technology and the impact it's having in the aerospace and defence sectors today. But first, can you share more about your background and your experience with metal additive manufacturing?
Yeah, hi Sam. Thanks for taking the time to talk to me and to talk about Norsk Titanium. Yeah, I left university with a degree in aerospace engineering and a doctorate in material science, and then started my career at Rolls-Royce in the UK, in Derby. Initially as a materials scientist, a materials technologist working in the Rolls-Royce submarines business, but then quite quickly moved into additive manufacturing, and I've been pretty much hooked on it ever since. So I was with Rolls-Royce for 10 or 11 years, and I finished up as the section leader for the development of additive manufacturing. And it was a really exciting time, actually. We led the first of Rolls-Royce's parts into series production. So I sort of cut my teeth on all of those first through the gate, and all of the problems with the regulator and with issuing internal specifications and building the business cases for those parts. And I'm sure lots of people working in additive manufacturing are familiar with that. And now I live in Norway, and initially I was working in the sort of startup environment in Oslo, and I was involved in setting up a startup called Pelagus 3D in Singapore, which was looking at digital inventories for maritime and oil and gas. And the company's fantastic and it's still going, so please, maybe you should talk to them in a future podcast. More recently I joined Norsk Titanium as the Vice President of Engineering.
Yeah, so you did that fairly recently, I believe. So when the opportunity to join Norsk Titanium as VP of Engineering came up last year, what attracted you to the position?
Yeah. So of course I'd heard of Norsk Titanium as one of the several DED sort of operating within the DED space. And actually, Norsk Titanium is quite unique in that it has an unusual value proposition. Most of the companies driving this fantastic innovation in additive manufacturing, whether it's laser powder bed fusion or binder jetting or metal jetting or whatever it is driven by companies seeking to sell machines. And then all of the burden of the qualification, like I just spoke about at Rolls-Royce, is on the OEM to then take that tool and qualify it for a useful purpose. In Norsk Titanium, we don't sell machines; we sell parts. So we have our own machines, but we have 3 plants manufacturing parts, but we've never sold a machine. We sell the parts, which means we have quite a unique position in the additive manufacturing market. So was of real interest to me when I was talking about the job. And one of the things that creates is a very strong domain knowledge within the company of how to qualify parts using additive manufacturing in complex OEMs and in highly regulated industries like aerospace. So we have a really fantastic engineering community here, and for me that's a very nice place to work with my interest and my background.
As you touched on there, Norsk is a supplier of parts, a tier 1 supplier, I believe, and is using it it's RPD technology, it's Merck series of machines to produce those parts. So in terms of the rapid plasma deposition process, can you explain the fundamentals of that process and the typical end-to-end workflow, I guess?
Yeah, so DED, direct energy deposition, there's several different technologies with different benefits. Typically, they're described by the raw material form, which is either powder or wire. So we're a wire-based technology, and then the heat source, and that can be laser or electron beam or just arc, like conventional MIG welding. And in our case, it's a plasma arc. And that gives us lots of technical advantages over those other heat sources, we feel. It's not just one heat source either. We have 2 plasma torches and 3 plasma arcs, very carefully controlled and covered by more than 200 patents. So the core of our technology is that hardware to deposit the material and control the thermals of that deposition very, very carefully so that we get the right mechanical and thermophysical properties within the product, and also the software that goes with it to pre-process the program, control the program during the deposition, and then all of the post-processing as well.
And I know a key benefit of a technology like your rapid plasma deposition process is to kind of get a part to near net shape. So I wanted to ask, how near is near, and how much post-processing is typically required to get to the final version that the end user is gonna use?
Yeah, so there are several post-processing steps. I think what you're referring to is mostly machining. In terms of how near is near to near net shape, technologies like laser powder bed fusion are typically nearer than faster, coarser technologies like DED, but we control our process so finely that actually we get quite close. So there's 2 things that feed into it. There's the surface texture. How much material do we need to remove to get to the bulk conforming material with no surface breaking defects, and then there's the consistency from part to part. We've had more than 3,000 parts in series production for the Boeing 787 Dreamliner. So by which I mean one part number has been made 3,000 times. So we really understand how consistent our geometry is. So we don't have to add lots of green to compensate for instability in the process. So we can get little more than a millimeter of green is needed on our process, which means good business cases, and then less machining afterwards, which of course adds cost.
And Norsk is currently on the 4th generation of its Merke machine, I believe, which obviously uses that RPD technology and is what you guys use to manufacture all of those parts as a tier 1 supplier. So on this latest generation of the machine, what are the kind of key capabilities and what are the new features that have been added onto this most recent generation?
Well, actually, the G4 isn't that new. You might call it a seasoned machine. It's hardworking and well understood and has been in production. I think we made the first one around 2015, and that's still here in Norway doing development work. As a bit of a workhorse, and then we stood up our first production plant in upstate New York in 2017, and then the second larger one focusing on commercial aerospace in 2019. And those 2 facilities have between them more than 30 G4 machines, many of them now running in series production for our customers in across different aerospace OEMs. So the machine itself, we have the G4A series, the G4B, which is transportable, can fit in shipping containers, and then to answer your question, the most recent development is the G4L, which has a larger base plate and a flip frame so that it can print on both sides of the substrate and compensate for distortion from residual stresses. So we have 2 of those now in the US facilities, and they're targeting large titanium rectilinear parts like you might find on, for example, pylons, where the engines connect to the wings.
Okay, in terms of printing on both sides of the substrate, what is the kind of operational benefit of of being able to do that?
It's mostly mitigating the effects of residual stress. So
Right.
the process induces a lot of residual stress because you have these rapidly cooling melt pools which contract, and even a very thick 1-inch base plate can distort significantly. So if we print one layer on one side or one set of beads or strings on one side, flip the frame over and print on the other, those compressive residual stresses balance out and compensate each other.
Right. Okay.
So we can print a completely flat part with deposition on both sides.
Cool. Norsk has established rapid plasma deposition as an alternative method of manufacture for titanium components, and I know you guys are exploring nickel as well. So when you look at this technology versus more traditional techniques, what do you see as the advantages of RPD, and when does it still make sense to go with a more conventional method?
I think it's a bit of a misconception that additive manufacturing will or should replace most conventional manufacturing. In most cases, the centralized conventional manufacturing works and benefits from large economies of scale, pioneered by Samuel Colt or Henry Ford or whoever. That still stands up. Really, in my experience, additive manufacturing fits in certain cases, as you say, and that might be 30% of the bill of materials or 5% of the bill of materials, depending on the industry. In our case, we know that we can replace a significant chunk of the titanium forgings going into commercial aerospace, but certainly not all of them. And I think in terms of identifying the right part, you have to firstly consider the nature of the individual part in terms of its material grade, its functional classification, how critical it is, and where it sits, and of course its geometry. Does it have a geometry which requires huge machining from forging in a very wasteful conventional process where we can get very close to near net shape? And then in addition to that, there's the softer benefits, which are often harder to articulate, around the security of our customers' supply chains and how we can support them in mitigating supply chain risk. Is the part manufactured from a forging which comes from Russia and carries huge geopolitical risk? Is it a legacy part which they don't know if next year they don't know if they need 1 or 100, and so they need supply chain flexibility to meet their own customers' demands from the airlines or the government in defense industries? So yeah, it's a very practical question about the part, and then a much more procurement business question about how additive manufacturing sits alongside conventional supply chains.
Okay. And in terms of the technology's maturity, you mentioned there that I guess you first started using this technology back in 2015. So over a decade. As you kind of look back over that 10 plus years, what has been achieved with this technology in sectors like aerospace and defense, and I guess what applications are you enabling, and what challenges are you addressing?
Yeah, so in terms of the technology's maturity, RPD is at TRL 9, no doubt about it. It's a fully commercialized technology. It's in series production. We're delivering parts every day that are flying around the world, and you and I have probably both flown on aircraft with our parts on them. In terms of the challenges we're addressing, I think it's important to think about composite aircraft, and composites replacing aluminium bodied aircraft has been a great shift within the aerospace industry. If you look at, I mentioned the Dreamliner, the 787, there's also the A350F, which are the two first big wide-bodied composite aircraft. Because they are composite-bodied, they have a much higher demand for titanium parts, where the composite meets the structural metal around doors, around structural areas, and irregularities in the airframe. So that actually, ironically, drives up the demand for titanium. And so, similarly, if you look at the demand for narrow-bodied aircraft now, Airbus are making, I don't know, 60, 70, 80 of those aircraft a month across their plants around the world. When those aircraft, I'm not just talking about Airbus, when those aircraft are replaced, they will likely be composite bodied. And there's a real challenge for the industry on supplying enough titanium. And so we are sort of stepping into that environment where there is a real demand and a supply chain challenge for titanium forgings in aerospace. And so we feel we have a strong benefit to bring there over the next decade.
Okay. In terms of working with those large companies in an industry like commercial aerospace, aerospace and Airbus and Boeing as a tier one supplier, I assume you're in quite close contact with people at those companies, on a daily, weekly basis. So how are they kind of driving your internal R&D efforts when it comes to the next set of challenges, excuse me, that they want to address? What is it that they're asking for?
You're right that we enjoy very close relationships at the engineering level with those big OEMs. So, for example, all of the big primes into the US Department of Defense, the wide-bodied aero engine OEMs, and the airframe aerostructures OEMs as well. And one of our strengths is that we have the engineering credibility to work hand in hand with their engineers. And the problems that we're solving together is typically getting through the qualification process to justify the use of RPD to replace forgings. Castings and forgings have been around for thousands of years. It's very, very well understood. The specifications are older than the people using them, and that's just not the case with additive. And we're the first through the door with RPD typically, so we're solving those problems with each of the customers, and that drives the R&D work that we do together. So it might be generating materials data for them to issue internal material specifications, process specifications, engineering specifications for our RPD process, which allows them to procure the parts. And then separately, we have our own internal sort of skunkworks engineering projects, which are really exciting, where we're trying to anticipate the customer's need and also maintain our market advantage. So we're really driving forward with our artificial intelligence and how we use that to characterize defects. How we will be able to use that to control the process is really not well understood. So we work with the regulators, with FAA, with EASA, because we're the only additive process approved by the regulators. So we are sort of working together with them as well to qualify those new technologies on behalf of our customers.
With that in mind, with all of the work that you guys are doing internally, with all of the conversations that you're having with those big names in aerospace and defence, what do you see as the kind of emerging application opportunities in those sectors for a technology like rapid plasma deposition?
Unfortunately, the way things are these days, the defence market is a big one for us. What used to be very stable supply chains with very long sales cycles and long procurement purchase orders for the defence industry has been turned on its head quite recently, and so the additional supply chain risk, the additional uncertainty, unfortunately plays into our hands because additive manufacturing can really help there. So we are gently and consciously supporting the defence industry with their urgent demands as well. So I think that's probably the most notable emerging application at the moment.
Okay. And finally, Jack, and thank you for taking the time today. Over the last decade and a bit, Norsk has kind of established itself as a trusted supplier of additively manufactured parts to the aerospace and defence sectors. What is next for the company? Where does the company go from here?
Notably, I mentioned our current platform is quite old and well proven. So there's exciting work going on what could be called the G5, the Generation 5 machine. Our current machine has 4 axes. So it's a gantry-based system with our proprietary print head, which then deposits with the substrate moving around beneath it. That makes it quite difficult to satisfy the requirements for axisymmetrical parts. So, for example, if there's a ring roll forging that requires features adding to it, bosses adding to it, that is a challenge with our current machine architecture. So that's something we're working on. potentially a fifth axis, which could increase the scope of parts we can manufacture for customers who are using axisymmetric rings and discs, for example. And also, we have an interesting challenge that as we're adopted more wholesale by our customers, if they transition fully to us, they will be going out of potentially one risky single source into another risky single source, because we're the only supplier of DED products this mature. So we have an ecosystem model or business model in development where we can supply machines into tier one suppliers, other tier one suppliers, to create a competitive market for using our technology, which will de-risk the supply chain for the customer. So they wouldn't only have to buy RPD parts from us, they could buy them from their existing suppliers with the RPD technology licensed or otherwise from us. And that's a really exciting area, more in the business innovation rather than materials and engineering innovation, which we're working on quite proactively.